Paper 2, Section A. Questions on organic reaction mechanisms demand precise, step-by-step structural transformations, clear representation of curly arrows, and underlying thermodynamic or kinetic explanations. Here are 3 highly selected, standard questions modeled on the UPSC Civil Services pattern with standard structural answer breakdowns. Question 1. Electrophilic aromatic substitution, orientation and reactivity. Q. Explain why chlorobenzene is ortho and para directing towards electrophilic aromatic substitution, yet it is less reactive than benzene. Provide the mechanistic rationale based on intermediate stability. 10 marks, model answer structure. 1. The paradox, dual nature of halogens. Halogens exhibit a conflicting dual behavior in electrophilic aromatic substitution, S_E, reactivity, controlled by the strongly electron withdrawing inductive effect, I effect. Orientation, controlled by the electron donating resonance effect, plus R effect, via lone pair delocalization. 2. Mechanistic rationale for deactivation, reactivity. Chlorine is highly electronegative. The strong I effect withdraws electron density from the benzene ring, destabilizing the positively charged transition state, sigma complex or uranium ion, compared to benzene. 3. Mechanistic rationale for orientation, ortho, para direction. When an electrophile, E+, attacks chlorobenzene, we examine the resonance structures of the resulting sigma complex for ortho, para, and meta pathways. Ortho and para attack. During an ortho or para attack, the positive charge is delocalized onto the carbon atom directly bonded to the chlorine atom. Chlorine can share its lone pair of electrons via resonance, plus R, creating an extra stable resonance structure where all atoms, including Cl, have a complete octet. Meta attack. During a meta attack, the positive charge never lands on the carbon bearing the chlorine atom. Therefore, chlorine's lone pair cannot be shared to provide resonance stabilization. 4. Conclusion. Because the sigma complexes for ortho and para attacks possess an extra octet complete resonance contributor, their activation energy is lower than that of the meta attack. Hence, chlorobenzene is ortho and para directing despite being deactivated. Question 2. Nucleophilic substitution and neighboring group participation, NGP, Q. Acetolysis of both erythro and THREO3 bromobutane 2-all yields racemic and optically active products respectively. Mechanistically explain this stereochemical outcome. 15 marks. Model answer structure. 5. Introduction to the phenomenon. The reaction of 3-bromobutane 2-all with acetic acid involves neighboring group participation, NGP. The neighboring bromine atom acts as an internal nucleophile, displacing the leaving group, or interacting with the carbocation, to form a cyclic bromonium ion intermediate before the external acetate nucleophile, OAC, attacks. 6. Mechanism for erythroisomer, enantiomeric pair, racemization. Step 1. Internal attack. The erythroisomer undergoes an intramolecular SN2-like displacement where the bromine lone pair attacks from the backside of the carbon bearing the leaving group, forming a symmetrical cyclic bromonium ion. Step 2. External attack. Because the cyclic intermediate is perfectly symmetrical, the incoming acetate ion, ACO, has an equal probability, 50:50, of attacking either carbon atom C2 or C3. Stereochemical outcome. Attack at C2 gives one enantiomer, attack at C3 gives its mirror image. The result is a racemic mixture, optically inactive by external compensation. 7. Mechanism for threoisomer, retention, optically active. Step 1. Internal attack. Backside attack by bromine in the threoisomer forms an asymmetrical, chiral, cyclic bromonium ion. Step 2. External attack. The opening of this asymmetric intermediate by ACO at C2 or C3 yields a single chiral product configuration because the intermediate configuration forces a specific orientation. Stereochemical outcome. Net double inversion leads to overall retention of configuration, rendering the final product optically active. Question 3. Elimination mechanisms, E2 vs E1CB, Q. Differentiate between E2 and E1CB elimination mechanisms. Predict the mechanism and major product for the base-induced elimination of 2-fluoro-1-nitroethane. 15 marks. Model answer structure. 8. Mechanistic comparison. Feature. E2 mechanism. E1CB mechanism. Kinetics. Second order, text, rate, equals K, text, substrate, text, base. Second order overall, but proceeds via a distinct carbanion intermediate. Timing of steps. Concerted, CH bond breaking and CX bond breaking happen simultaneously. Stepwise, CH bond breaks first to form a carbanion, followed by slow loss of the leaving group, X caret. Requirement. Good, moderate leaving groups, anti-periplanar geometry. Poor leaving group, highly acidic, alpha hydrogen to stabilize the negative charge. 9. Analysis of 2-fluoro-1-nitroethane. Substrate factors. Strong electron withdrawing group, EWG. The nitro group, text, No_2, is exceptionally strong at stabilizing an adjacent negative charge via inductive and resonance effects. This makes the protons on C1 highly acidic. Poor leaving group. Fluorine, text, F, is a notoriously poor leaving group due to the high strength of the CF bond. 10. Stepwise mechanism, E1CB. Step 1. Fast equilibrium. The base removes an acidic proton from the carbon attached to the text, No_2 group, generating a stable carbanion, enolate-like intermediate. Step 2. Slow, rate determining. The lone pair on the carbanion expels the poor leaving group, text, F, to establish the carbon-carbon double bond. 4. Major product. The major product is nitroethene, text, O_2, text, N, text, CH, equals, text, CH_2, formed explicitly through the E1CB mechanism. Would you like to review another specific class of reactions or mechanisms for the optional paper? Pericyclic reactions, FMO method, name reactions, e.g., Beckmann.